Hello, everyone. Hope you're doing well. We're in another location today in a nice outdoorsy kind of way. I am up in Kentucky right now, and so I wanted to go out and enjoy a little bit of the sunshine while my family rests upstairs, and they don't have to listen to me talk about functional vector spaces today, although I know they'd be dying to hear about it. In particular, we have two very exciting examples to talk about today. We've talked about how this chapter of what we've been going through is a little bit more concrete than the ones that we've been looking at from before. Chapter 3, we dealt with a lot of just metric spaces in general, whereas here we're going to start taking a look at particular types of vector spaces, which consist of functions. In this case, functions between two other metric spaces X and Y, as you see here in these kind of formulas given up here on the title of this page. You might even be able to guess what B stands for or what C stands for, because we've seen C before. C of XY is the space of all continuous functions from one metric space to another. But the notion of continuous functions is really most useful whenever you're starting from a space that is compact. To say for you, when your X is compact, you know that your continuous functions are bounded. And if you know that they're bounded, which we'll talk a little bit more about today, then you can say a good bit more about what's going on with the types of functions that you're working with. And so we're going to be dealing with exactly those types of sets today. Either B, the bounded set of functions from X to Y, where these are not necessarily continuous, or C sub B, which we have sometimes we'll see actually written as BC X comma Y, which is the space of bounded continuous functions. C sub B, think of it as like adding to the space of continuous functions another parameter. That any function that has to be inside of the set must also be bounded. Here, X and Y, we're going to experiment with a couple of different metric spaces here, but we'll see some examples of what happens when X is compact and when X is not compact. Then something that we're going to focus on here in the video lectures that I didn't see a ton of in the reading assignments is we're going to focus on the size of these sets, and we'll give a couple of different ways of kind of visualizing how big these sets are. And this is going to be something that holds true regardless of what the spaces X and Y are. And we'll see a little bit more about what happens as we kind of go through and discuss what happens with these particular spaces. But first, let's go through and understand what these spaces are as is, starting with the space of bounded functions. So that defining this real quick, we will say that the function f of x comma f of x to y is in this space b of x comma y whenever there is an m in the real numbers such that the distance between any two y values of the function is less than or equal to that predetermined value. This needs to be something that holds true for all values of x and y inside of the set X. So when I'm thinking about this, I start thinking, okay, well, how can I start thinking about defining a metric on this space? Well, the first thing that I could go through and do is say, okay, well, I'm going to define a metric to be kind of similar to something that we've seen already. We've discussed how for the space of continuous functions, starting from a compact set, that you could define a metric on that, like continuous functions from 0 to 1, for example. You could define a metric to be the supremum over all possible x values of the distance between y values of that set when plugging in those specific x values. And the question is, how do you know that these two types of functions are even close to each other? How do you know that they kind of are, that this metric, for example, is something finite? What are the sorts of connections that we can make there? And so this does involve a little bit of a theorem. So I've gone through and kind of constructed a quick proof here. Now, this sort of proof you may have already kind of gotten an understanding or an intuitive understanding of in your head because you've seen how this sort of thing works for continuous functions. The only difference between that proof and this one is that we don't get to use some of the nice things about continuity that we had from before. But essentially, a lot of the sorts of language that we might use stays the same. In particular, instead of just using this particular example, we could have even given a different way of thinking about it. One way of thinking of it is this. Say, for example, that you want to find the distance between f of x and g of x. Between these two different y values. And something that you might do is you might attempt to utilize a triangle inequality here. Triangle inequality saying the distance between this and f of x to say the point 0 plus the distance between 0 and g of x. This is something we're absolutely allowed to do. But then I claim that we can replace each of these distances with exactly the values of m that we were talking about before. The capital M, the one where we talk about how big the y values can possibly get, because this is essentially saying that the largest possible way that you could get this value to be is going to be less than or equal to whatever kind of bounded constant that I can get from the definition on the previous slide for the function f. because this distance between the y value of f of x and the y value of 0 is going to be at least some value like this. Now, the issue with this sort of way of approaching it, though, and this is where we have to be a little bit tricky with it, is the m sub f value that we got there was something actually that told us the distance between possible y values of our function is bounded by this value of m, and our function does not need to have a y value of 0. So you could see a little bit as to why we have to kind of deal with this a little bit more carefully, utilizing this sort of approach. Now, some people actually do define bounded functions just as I have described. They might say that a function f of x comma y is bounded, and in fact, we probably have done this somewhere else in this course, if you could say that the largest possible distance supremum of all x and x, of the absolute value of this distance of f of x to some point like 0 is less than or equal to this m. Now, why am I not going to finish writing that, though? Because when we did that in a previous part of this course, we were assuming that we were working in the real numbers for this space y over here. But because this metric space y does not need to have a 0 in it, I can't actually write 0 over here. That would not be a right way to kind of write that sort of statement. So I do need to be a little bit more careful in that. So you might look at this proof and think, oh, this seems like to be a little bit extra inside of here. But the truth is actually using the fact that we don't quite know any of the elements inside of the set Y. So I can't actually write this element of 0 inside of here. This is something that doesn't quite make sense. So I could, if otherwise, if I were looking in terms of the real numbers, then I could say, take the boundedness constant for f, take the boundedness constant of g, and then add those together, and you get this sort of finite metric here between any two functions, f and g. But instead, what I have to do is fix a particular kind of point inside of my space of x, some x value there, and use that as some sort of boundedness coefficient generator, something that creates my m sub a and n sub a. Then the rest of it essentially comes from the fact that I do get to have some sort of finite addition of all of those different values here. I do have to add in this little kind of difference value between f of a and g of a here. But other than that, this is essentially the same sort of notion of boundedness as what we would work in from the real numbers. We just have to be a bit more careful because we don't have access to a 0 in our spaces. Nevertheless, we still get a finite metric here. And in fact, if the metric returns a value of 0 when you plug in two functions, then that means that the distance between any two functions at any of those particular x values must be 0, which means they must be the same by definition of metric. Finally, we can go through and do a triangle inequality, just like we would hope to, but this is a nice little trick that I also use a little bit up in here that I want to kind of emphasize. It's a little bit more clear on this bottom line, so I'll focus on that. Notice here that I'm saying, let's take a function functions f, g, and h that are all bounded. And notice that I can, by the fact that I have a triangle inequality on my metric, break it apart so that f of x and h of x can be intermediated by this g of x. Now, the row distance, the row being the thing that I defined on the last slide, that row distance between f and g is the supremum of all values between f of x and g of x over all values of x. So this less than or equal to definitely holds for this term. And then there's a less than or equal to for the second term as well for a similar reason. What I can do at this point is start doing something called taking a supremum over all x of both sides. Now, what does that mean here? Let's say, for example, that I know that the stuff over here on this left-hand side, in terms of x, is less than or equal to this guy. Well, something I can do is say, okay, the x variable here is something that's allowed to range between all values of our capital X, our domain space for our functions. So something that I can do is ask what happens if I take a supremum over this set. If I do that on the left-hand side, that's the same thing as allowing me to do it on the right-hand side as well. The inequality is still kept here. The reason is, if I allow x to range here on the left-hand side, and if I allow x to range here on the right-hand side, then I'm going to get the largest possible of all of the x values here, which is still going to be larger than one of the x values that is given over here. So that's something that is a neat little thing of kind of like apply to both sides, the supremum, kind of like how you would add something to both sides or divide something from both sides of an inequality. Taking a supremum of both sides is something that is absolutely valid. You might remember some of this stuff from looking back at your undergraduate analysis course, if that is something in the proximity of your memory, but just kind of something as a refresher. But what's interesting about that is that there's no x over here on the right-hand side. So what's the supremum for over all x and x of something that's a constant with respect to x? Well, it's just going to be that thing. So what is this saying really then? The thing on the left, now that I've taken a supremum, is now the distance, the row distance between functions f and h by the definition of row. And on the right-hand side, I have row of f comma g plus row of g comma h, which putting this all together gives us exactly the triangle inequality. So that's what is meant by taking the supremum over all x on both sides. In fact, that's a step that I actually had to take over here as well. You might kind of try and dig through that a little bit to see where that was utilized too. So this gives us something that is a metric on this space. So that b of x comma y can indeed be a metric space, and that all of the things that we've been discussing for metric spaces start applying to this space of functions. Knowing that functional metric spaces exist is a big deal for us, because having something like a metric apply not only to things like the real numbers, but to functions allows us to treat functions as vectors for us. And that's a really huge deal for Fourier series and things like this. It says that we can apply context for vector spaces onto these things as well. In some future videos, we'll talk a little bit about how we can start looking at certain orthonormal bases and kind of apply that a little bit with some of this density argument to get something really neat in terms of approximations. In fact, by the end of today, we'll see that we don't even need the vector space component of all of that. We just need functional metric spaces. It's not even a kind of a vector space structure to it in order to do some of the things that we discuss. But another thing that's important to us for some of the theorems that we've been discussing so far is that our space be complete. B of x comma y be a complete space. And it turns out that that's not necessarily always the case. We want to be clear that this is something that happens. So to do this, first things first, we'll discuss what it means for sequences of functions to converge inside of this space. Well, remember that we're given the same metric as we had back in the continuous functions from x comma y in that space. And that's, we had a theorem from last week that said that if sequence of functions converges inside of C of x comma y, if and only if they converge uniformly. That's essentially the proof of this proposition. A sequence f sub n converges to f and b of x comma y, if and only if it converges uniformly to f. So that's going to allow us to determine whether or not a space is complete. Remember, we say that Cauchy sequences converge. We need to show that whenever you have a sequence of f sub n that is Cauchy row, that is that row of f sub n comma f sub m grows to 0 as n and m go off toward infinity or past a certain cutoff point. So this will be less than or equal to epsilon at that point then. Then we need to be able to show that there exists a function f that is also a bounded function going from x to y, such that the distance from f span of f goes to 0 as n goes toward infinity. Okay, let's see if we can do that. We're going to have to think about an arbitrary collection of functions that is Cauchy row. That means that the distance between them, and in fact, the supremum over all x values of f sub n of x and f sub m of x, that those distances growing small means that there is some sort of way to define a function. And it turns out that the only thing that we need in order to make something like that happen is we only need the values of y to be complete. And before we get into the proof, let's talk a little bit intuitively as to why that might be the case. The codomain y being complete allows us to define this function f. Now, to define a function f, what do you have to do? You have to assign to each x value of the function a y value. Now, note that each of the functions that we start with in the sequence, f sub n, f sub m, those all already have y values. And for them to be Cauchy in this, we need to be able to, it allows us to say that there's a uniform nature to the sense that for all x, f sub n of x minus f sub m of x is less than epsilon. Now notice that these are both elements inside of y. In fact, I'm writing the absolute values here, and I shouldn't be. I should be writing the distances in terms of y. So good self-correction there. So both of these things are inside of y. And if we know that y is complete, then I might notice that just fixing any type of x for all x, that the sequence f sub n of x is Cauchy in y as a result. And if I know that Cauchy sequences in y converge in y, then perhaps I could define the function f of x to be the limit as n goes to infinity of f sub n of x. So for all x values, perhaps I could go through and show that it is well defined for me to take a function whose y value at a given x is the limit as n goes to infinity of all of the Cauchy sequence values that are around it. The goal, of course, is going to be to show that that function is still bounded. We have to show that that f is still inside of the space. And then finally, that we get this row convergence as before. Because we're only defining this pointwise, so does this work when I consider coming back to all of this? Do I get a uniform convergence of these functions converging here? And that's essentially the ideas behind this proof. For all of the types of ideas that are given there, this is indeed a good bit short. And that's kind of neat to see. I think there actually is another slide, so I should, nope, there's not. So this is all it is. That's good enough. So starting here, let's take our Cauchy sequence and construct this function f. We know that we can get this distance between, for any x value, this distance in y between any of the y values here, to be bounded above by this value of rho between any two functions. So if f sub n and f sub m are Cauchy, this rho of f sub n comma f sub m grows to be very small. And that gives us that f sub n of x is a Cauchy sequence. Y is complete, so it converges to a point, and we define the function to be that limiting value. Well, we can now get that f sub n converges pointwise to f without having to do any work, because we said for all x, this sequence of Cauchy values converges to this point. So that's automatically converging pointwise. But I still need to show that it converges in rho, that it converges uniformly. So hence you see that that's part 2 as well. And then part 1, I needed to be able to show that the function is indeed a bounded function. Let's start with showing the uniform convergence nature. And what's going to play a part in this role is the fact that this rho of f sub n comma f sub m is something that's constant regardless of the value of x that I choose, and showing that something is uniformly convergent. Recall that uniform convergence doesn't really care about the value of x. It wants the epsilon delta values to be the same throughout the entire interval that you want your convergence in. So let's do that. Let's fix an epsilon greater than 0 and take a function, this sequence of functions that is Cauchy. Then there's going to be a cutoff point where this distance in y between f sub n of x comma f sub m of x is less than epsilon over 2. And notice here that I never had to specify an x value. This is something that's going to be true for all x inside of x. And that's because of the fact that f sub n is in some sense something that we might call uniformly Cauchy. I don't know if we've actually used this term before, but it's the same sense in which you might say something is uniformly convergent. Uniformly Cauchy, the only difference is that the sequence of functions that you have is Cauchy in the sense that when you take every given point, each point gives you a Cauchy sequence with the exact same epsilon and delta values at any given point of x. So that's what's meant here. These functions f sub n are uniformly Cauchy. Then the difference in these y values and f of x can be broken apart as a limit as m goes to infinity of this distance right here, less than or equal to epsilon over 2. Here, what we're doing is using the fact that the distance functions values here between f sub n and f should be a limit value of f sub n and f sub m. So how are we going to get to this point? Because remember that metrics themselves have to converge or diverge from something continuously. This is kind of like using a continuity argument here. We know that for this value over here on the right, the limit as m goes to infinity of f sub m of x is equal to f of x. But we're allowed to take that limit outside of the metric here because the metric is continuous due to small changes inside of our function. Just because of the same, almost in a tautological sort of way. If I make small changes in my function, then those small changes are small with respect to the metric. That's what I mean when I say a small change. If f sub m converges to f, it converges to it with respect to the metric. So this is kind of where we're allowed to take this limit outside this. So, but what this tells us is that the distance from f sub n of f to f at any given x value is actually less than or equal to epsilon over 2. We now take a supremum with respect to x on both sides because we can, essentially doing this sort of argument that we've done before, to say that this supremum of these distance values here, which is exactly rho of f sub n comma f, is less than or equal to epsilon over 2. And the only reason I needed to use epsilon over 2 this whole time was to get something that was less than epsilon eventually. And that gives us the uniform convergence. And so part 2 is done. The last thing I need to do is show that this function f is a bounded function. And the way that I'll do that is using the fact that I can basically use the function f sub n as an intermediary. The function f sub n is bounded. Any sequence that I'm using to converge to this function f that I've constructed is a bounded function. So there's a bit of a triangle inequality that I can construct then. That the distance between f of x and f of y, which is exactly what I need to show is bounded here in order to show the function f is bounded, is controlled by the difference from f of x to f sub n of x and f sub n of y and f of y, together with the distance between two y values inside of the function f sub n, which are always going to be bounded because we assume the sequence f sub n to be bounded. That's what gives us this value of m. The two row f comma f sub n comes from the fact that I know that these are going to go towards zero, and that in fact they are controlled by the row convergence that I have just established back in condition 2. So because of this, I'm able to say, I'm putting some y subscripts here because I forgot them. Because each term over here on the right-hand side of this inequality is going to either be bounded in the sense of m or go towards zero, like this guy right here, I should be able to say that after taking nope, no need for a supremum. No, yeah, actually, taking a supremum over both sides for all values of x and y, that any value here is going to be bounded, and that gets me what I'm looking for here. So pretty neat stuff. This tells us that even if you just have the codomain as complete space, then b of x comma y is something complete. And again, we want to have complete spaces so that we can get convergent functions whenever we're looking at something that's getting closer and closer to a certain point. It allows us to know that some of the properties and theorems that we look at very strongly for other types of spaces, namely thinking back to things like Stone-Weierstrass or other things that don't involve this sort of distance metric. So thinking of things like extreme value theorem and things like this, and all of those other theorems we talked about back in week 2, that those things can keep applying a little bit with these complete spaces, at least in the senses that we have them, because metric spaces only have so much structure. We're trying to take those same concepts and apply them here because they share the notion of completeness. But something that we don't talk a little bit about in our textbook here is how big this space is. And so I think this is a good question for us to be asking as we go through spaces in this particular video lecture, which the question is this: is b of xy manageable? Now, what do I mean by manageable? Is it something that I can essentially deal with by looking at something that's a little bit more clear? Now, let me give an example of something that I'm using manageable here, because this is definitely not an actual definition here in mathematics. It's just something that I'm using to give an idea. Let's take the real numbers, for example. The real numbers is a manageable space. Because even if there's so many elements inside of it, even though it is an uncountable space, there's at least something inside of it that is countable, but essentially gives me the main idea metric wise as to what is going on inside of the space, and that's the rational numbers. The rational numbers are a countable dense subset inside of the space. We've defined dense before. It's to say that the closure of the set of the rational numbers is the real numbers. So when I'm saying manageable here, what I'm really meaning is something like separable. Separable here meaning that you have a countable and dense set inside of your metric space X. Countable, remember, is something about size, and dense is something about distribution. It's saying this is saying how many are there, and this one's saying where are they? So countable dense means that essentially you can, even if your space is uncountable, you can at least manage it somehow in terms of something that is countable. It's like the rational numbers. So the real numbers are separable since the rational numbers are countable dense in R. Essentially, this measures how much space a metric creates inside of a metric space. It is relatively hard to converge uniformly, meaning that fewer functions are close to each other. Set being separable implies that every function is close to a countable set. So although the set itself may not be countable, it is at least close to being one under its metric. So let's show that the bounded functions from 0 to 1 are not separable. Let's start there. First, notice that this is a bounded set over a compact interval, something like 0 and 1. But that's all that I need to take the set and make it not separable. That is, let's show that there is no countable set in B01 such that its closure is all of the set B01. If we get to do that, then we have essentially shown that this is a very weird space. Now, this notation that I'm using is not this notation of b of x comma y. So let me rewrite it. in a way that makes sense. Whenever I write something in this form, typically I mean for its range values to all be inside of the real numbers. So this is what I mean when I write that sort of set. Okay, so let's see now. I want to show that this set is not separable. Let's think about what it means for two functions to be far apart in this space. For two functions to be far apart, their row value needs to be pretty big. That means that there needs to be at least some point between the two functions where the difference between them is 1. Okay? So, for example, we could consider the set f of x equals 0 and the set g of x, which is just the continuous the characteristic function of the set, which is just 0. That is two functions whose distance from each other is equal to 1. F of x equals 0, where it's 0 everywhere, and g of x equals the characteristic function, where it's only equal to 1 at the number 0. That because the row metric takes a supremum over all possible x values, the largest possible distance between these two functions is 1. So because of that, row of f comma g is equal to 1. I could even multiply this number by 5 and get that this metric is 5. So you see here that even just a change at 1 point changes the metric potentially between these two functions dramatically. And that's exactly what we're going to utilize in this argument here, is that we can just change very little about this space and get something that is very, very different from it. So here's what I'm going to do. Here's my goal. I'm going to form an uncountable set of functions in B01 such that the distance between any two functions in there is equal to 1. And that's going to be for all fg in this set. Now, how does this goal show me that this set is not separable? Now, remember what separable means. It means countable and dense. So if I form an uncountable set of functions, think about what that means. It's saying that there exists some functions that regardless of what countable set that I might choose, if I try and say, okay, we'll take that countable set and consider all of the functions that are close to it. Well, for example, any countable collection of this uncountable set of functions, there are still uncountably many functions that are far away from this countable set that I've chosen from this set. Well, John, what if that countable set was somewhere else? Well, then we could use a triangle inequality with rho to show that they're still far away enough from each other that shows that this does not work. So a neat little thing that you might try and go through to try and understand why we're doing this particular argument here is to clarify this exercise. Show that this implies B01 is not separable. And the way that you might do this is you might actually try and do a contrapositive argument. Say B of Z01 is separable. Then say that there cannot exist this uncountable set of functions. If you negate that sentence, what does that look like? For all uncountable sets of functions, or for the entire space itself, right? So try negating this statement. So hint, the negation should look like for all functions in B01, or rather, I suppose I'd have to go back and take a look at it a little bit. But essentially, it's saying that the functions are close enough to some sort of countable set. So I'd have to go back and take a look at that a little bit. So I'll leave that kind of think of forming the negation here of this statement. So let me just write that instead. Form the negation of the statement that starts, there exists an uncountable set. And see if you can figure out how you might be able to find this sort of countable set. The idea, again, is that if there's uncountably many of these sets all far enough away from each other, then what's happening is no countable collection could be close enough to all of those functions in that uncountable set because they're all so far away from each other. So there's no way that you could get something that's close to each and every one of those functions. So let's go through and satisfy this goal first and say that that's what we're trying to do. So let's do it. Form an uncountable set of functions here. Here it is. Let 1, comma, r be the characteristic function of the set R, where R is a real number inside of the closed interval from 0 to 1. And that's it. This is an uncountable collection of functions. That uncountable collection of functions I know is uncountable because I have a function or a set of all values of functions between 0 and 1 as my indices, and I know that my indexing set is uncountable. What's more, the distance between 1r and 1s is equal to 1 for all r not equal to s. So because this is an uncountable set, this gets us everything that we need to accomplish our goal. I did pause the video for a little bit to think a little bit more on my hint here. So I'll go ahead and kind of erase a little bit of this to think a little bit to say a bit more about what I ended up thinking about. So let's say a little bit about what's going on here. So my hint is this. Consider the set of open balls of radius 1/2 around each of these functions. So think about each of these open balls that are happening here. So think a little bit about this and see if that kind of hint kind of gets you some sort of direction here, just gets you something a bit more in this direction to see a bit more as to why this is good enough. These open balls, notice, are not going to be containing any of the other functions in there. So think what has to happen here with a countable dense set whenever I'm trying to think of this. So work with this sort of notion. Remember, we talk a bit about how this sort of open balls stuff works a lot, what works very well in some topological contexts. Think about it here for this hint here too. Let's move on to another collection of these functional vector spaces, looking here at the bounded continuous functions. We saw in our last example, b of x comma y is a very large set. And the issue stemmed from the fact that we could basically define functions however we want. Probably you've never seen functions that are of that particular form before. That is characteristic functions that are only one at a very particular point and 0 elsewhere. That's because our definition of a function as analysts is as assignments, not formulas. I make that distinction here because historically speaking, and that analysts use, we're thinking of functions as things like cosine of x, sine of x, x squared, all of these things that we find that in some sense feel a little bit more natural. In some sense, it's just because we've seen them a lot more, but also because they came from types of applications that were very useful there. And then suddenly characteristic functions became very useful. You may guess as to where, in solving partial differential equations. And that became something that said, okay, well, we want this to be a function. You can look around to see what some of the controversy was in defining something called the Dirac delta function, which is a function that's literally 1 at a specific point and 0 elsewhere. And there was a whole debacle about whether or not to even consider that as a function. But with including functions like this here, we get that the bounded functions is a huge set. It is not manageable. It is rough to think about. So even bigger in some sense than how we might consider the real numbers in relationship to the rational numbers here. So let's make our study a little bit more strict, why don't we? Let's try and add another condition to the bounded set. Let's ask that our functions also be continuous. Notice that none of the functions that we used from before were continuous at all. Those functions were very much take a blip, go somewhere, and go somewhere else. No way to pick up your pencil or draw that all without picking up your pencil. We are now going to ask for that to be an extra condition. And we're going to ask a few questions now about this statement. Is this going to be the type of set that we look for that's a bit more manageable? Did we shrink up the size of our set enough for it to be separable now? Think of that as a goal as we start moving through this. Well, first, we want to show that this space is very similar to the other one in the sense that it is also a complete space. But recall that we've said that closed subsets of complete spaces are also complete. And so we could go through and just show that bounded continuous functions are themselves closed in the bounded sets. And what that is, that proof of that proposition follows directly from the fact that the metrics between these two spaces are, one, exactly the same, and two, the convergence underneath that is uniform convergence. And remember that we said that uniform convergence of continuous functions is continuous. So if I have a sequence of functions f sub n that converges to f in this metric row, then they converge uniformly. So if the f sub n are continuous, even if I don't know if the function f is continuous yet, which I would need it to be in order for it to be closed, then I would say, okay, well, I could just utilize this fact. Convergence in rho is uniform convergence, and the uniform limit of continuous functions is continuous. So the limit of f, this f is indeed inside of the bounded functions. That says that since f was a limit point of C sub b, that it is indeed in C sub b, which is exactly the definition of closed. And we get an immediate corollary from that that says if x and y are metric spaces where y is complete, then the bounded continuous functions from x to y is also a complete space. Okay, so we've got another complete space to work with, and we know that this is going to be at least a strict subset of this. In fact, we found uncountably many functions that are outside of this space. And I'm not going to go through and try and make a claim that this is a countable space in any way. It still seems like you could do a similar thing where you make, even if the points you're choosing for your functions here aren't all just like blips up and blips down, that you could still make little, you know, kind of triangles to go up to each and every one of those different points. So you could still imagine uncountably many continuous bounded functions, even on the interval from 0 to 1. But I am curious if now we've gotten something that's separable. Have we gotten something that's easier to work with or more manageable in terms of space? So let's keep going as we talk about this. First, we kind of maybe have discussed this a little bit, although I'm not too sure. Let's kind of go back through this theorem just to be super clear. That says that if you have the space of bounded continuous functions like you have right over here, then in fact, you have that's the exact same thing as just the continuous functions. And what is the relationship between these two sets? Well, one set does not have a bounded constriction, but we're claiming that if x is compact, that's exactly the same as the bounded continuous functions. What we're attempting to say by saying those two sets are equal is that every continuous function here in this left set is actually a bounded continuous function. Every continuous function on a compact set is bounded. Now, think a little bit as to why that's the case. The essential idea behind that is that the extreme value theorem here should still hold in this context. To be clear here, we've gone through and said this a little bit in one of our previous videos. Not this one anymore. It's going to be this one's 4-3 video lectures. If f is continuous, then f of x, that is x being the domain space, is a compact set itself. But compact sets are totally bounded and hence bounded in d sub y. Since the range of f is bounded in y, f is a bounded function by our definition of bounded that we had from the beginning of this video lecture. So this tells us that continuous functions on compact sets are automatically bounded. Pretty neat. So we don't even have to write C sub b whenever we have a compact set to begin with. And in fact, we're going to see in a little bit that we actually want to be dealing with only compact sets here, because it turns out that if you even add in something that's non-compact here, like the continuous functions that are bounded from the reals to the reals, that you still get something that is not separable. So let's see if we can figure that out utilizing a diagonalization argument. So we've seen quite a few diagonalization arguments in this series now, and it's pretty neat to see them all doing very different things. But I've mentioned in the last time that we did it that diagonalization arguments appear in a surprisingly proliferative number of places in analysis, and it does appear here in a different way than it did from before. Previously, we used it to show that the set of all contractions of functions going from 0, 1 to -1 to 1, that all set of contractions for this were, and that was a compact set. And the diagonalization argument helped us out here. Now, here's another one. Let's let f sub n be a countable subset of c sub b. And let's use a diagonalization argument to construct a function where the distance between this function f that we construct and any of the f sub n in our countable subset is going to be greater than or equal to 1 in distance. Now, what does this say? This says that if you have a countable subset, no way can it be dense. Because why? If you have this function f, if this set were dense, then there should be some sequence of elements inside of your countable subset. So think like a subsequence or something like this that converges to the point of f. But that subsequence cannot converge to f if every single element inside of that countable subset is at least one away from the function f. And in fact, you can see here in small font, I've gone ahead and added another condition that we get just as a result of working through this proof. You'll actually be able to see that we don't even have to make the function f go very big. We can actually say that the absolute value of the function, the y values of the function, can be bounded by -1 and 1. That you don't have to go pretty crazy in that. So let me show you a little bit about how we might start constructing this. So let's construct a table. And here's how we're going to do it. I'm going to put as my rows of the table F1, F2, F3, F4, which is me just enumerating the countable subset here. I'm going to enumerate the entire countable subset that I'm working with here. Because it's countable, I can do this. I can put them in a list and I'll put them vertically. Then I'm going to put the natural numbers right up here. 1, 2, 3, 4, 5, so on and so forth. And what I'm going to do on the inside here is I'm going to put f sub n of k, where n is the index that comes from what row that I'm in, and k is the number I'm plugging into the function and also the label of the column that I'm given. So this, for example, is f sub 1 of 2. This is f sub 2 of 1, f sub 2 of 2, so on and so forth all the way down. And I will fill in my entire table like this. Now here's what I'm going to do. I'm going to construct a function f that is still a bounded function in the following way. Construct f like this. So that for all natural numbers here, in fact, I should probably use a different letter than n. I'll use k. For all k in the natural numbers, that 1 absolute value of f of k is less than or equal to 1. And 2, that the distance between f of k and f sub n, f sub k of k is greater than or equal to 1. Now, let's think about what I've just written here as far as that construction. The difference between what I've written here in blue and what's written there in the problem box is that I'm specifying a particular x value to be plugging in for each of these functions. I want f of k and f sub k of k to be at least 1 apart from each other. K here is just some natural number. So for example, if I plugged in k equals 1, then this is saying I want f of 1 to be an absolute value less than or equal to 1, and I want the distance between f of 1 and f sub 1 of 1 to be greater than or equal to 1. Now, how could I do something like that? There's actually enough room for me to work here with this restriction to further claim that my absolute value of f of 1 is less than or equal to 1. Because think, even if f sub 1 of 1 is a y value like 0, then I actually have two values that I could choose for f of 1. I could choose f of 1 as 1. I could choose f of 1 equals -1. And all I'm going to do, at least at this point, for defining that function is just define, in that case, for example, if f sub 1 of 1 is equal to 0, define f of 1 to equal 1. That's all I'm going to do. And then if f sub 2 of 2 is equal to something like -2, then I have even more room to run. In fact, at that point, I have the entire interval to define f of 2. And I can make it any number in between -1 and 1. I might just choose 0. What I'll do after that point is, finally, connect the dots. Because what I've done at this point is I have created a function that is defined on the natural numbers. Maybe it looks a little something like this. And I'm just going to make it a continuous function by just going through and connecting all of the dots that I've made here for this function. The function needs to be defined on all of the real numbers, so I'll just go through and connect it back to 0, and then I'll make it 0 everywhere over on the left of it. So what's unique about this function? I have gone through and defined it as a function where I connect the dots of everything I've defined. And notice that my diagonalization argument is this. I have asked for the function to be at least one away from all functions on the diagonal of this table. What does that mean in terms of the metric? Remember that the metric says that's the distance between f and f sub k is going to be greater than or equal to the metric of it at any of its given points, including at the point k. But I know that I've just defined that metric. Just defined this function f in a specific way so that at the value of x equals k, that the difference between those 2 points is greater than or equal to 1. So the row distance between the two functions themselves, being the supremum of all possible x values, is greater than or equal to 1. And that's exactly what I wanted to show. So not only was I able to construct a function that was bounded by less or equal to 1, that was also continuous, as you could see from our picture down there, but I also was able to construct it in a way so that it was at least one distance away from any other function. And based off of our argument that we made before we started all of this, that's enough to say that this function is indeed, or that this set is indeed not separable, that this set is once again huge. As big as the bounded set was, and going back down to the bounded continuous functions here, looking at this from the set of bounded continuous functions from the reals to the reals still generates a huge number of functions, so much so that it is not a separable set. So we've shown two non-examples of separable functions, and gratefully I wanted to do this. I've shown it that it's not separable in two different ways, right? One example, I used a different version for non-separability than I did right over here using diagonalization. But how are we going to get to something that is separable? And that's where this Stone-Weierstrass theorem comes in. This is something near the end of our reading here, and I'm going a little bit out of order to our reading assignment here because I want us to kind of keep going on this thread of showing the size of these spaces. How big are the spaces that we're working with? And the issue here is that the real numbers as a domain gives us too much room to run. We can keep making functions that kind of keep popping up and over and over and over, that they're always at least some distance away from any countable set that I might generate. So that's exactly what we end up exploiting in the argument that we had on the previous slide. Notice that this argument would not work well in another type of set. If I have replaced the natural numbers with something like the values 1 minus 1 over n, then the f of x of n converges to f of 1. So the function f that we construct may not even be continuous in that sense. And indeed, that ends up kind of making our whole argument a little bit uncertain. Something that's hidden there that we may not have noticed as we went through that is that it is important that the natural numbers is a discrete set inside of that space and that there's no possible way for it to converge in any way. Since x of n is a bounded set, anything that we could replace it with, any sequence inside of a compact set, for example, would have to have some subsequence that converges. Well, since that subsequence is going to converge there, we would have to ask a little bit about that continuity. So what happens if we now replace the real numbers in that example with something that is compact? Do I have something there that helps me out? To help us here, we have a theorem. And that theorem is what we saw, I believe, in section 4.10, 4.7.8, something around in this range of called the Weierstrass theorem. This is not the Stone-Weierstrass theorem. This is the one that simply says the polynomials are dense and the continuous functions from the closed interval from a to b to the real numbers. Now, the polynomials are not a countable set, but we'll see in our homework that there's a way to get a countable collection of polynomials that essentially has that same density argument. And what we're going to be able to claim after all of this is that this set here is a separable set, that this is manageably small. Again, this is equal to C sub b of a comma b comma r, because we could think of all continuous functions on a compact set as bounded already. So that's kind of where that sort of thing is coming from. We're just kind of making a variation on the same sort of set. So we give two proofs of this theorem in our reading, and the one is given in a more probabilistic sense and may not be too accessible unless you've maybe seen Chebyshev's inequality before, or you've played around with a little bit of polynomial or probability theory, in which case the expected value sort of stuff probably does not throw you for a loop. But instead of focusing on the proofs here, what I'm going to do is talk a little bit about what the power of this is. What is it that actually comes as a result of these functions? So let's take a look here at this exercise. Let's let f be a function from this closed interval a comma b to the real numbers, and let's ask that it is continuous such that the integrals from a to b of f of x times x to the n dx is equal to 0 for all n values. And let's show that f is indeed equal to the 0 function. Okay. We need a lemma for this first. The first lemma is going to be this. If f is continuous and f is greater than 0, the integral from a to b of f of x is actually greater than 0. This lemma may not be a surprise. If f is a positive function, then there's actually a point there that the integral of f of x is greater than 0. But notice that I need continuity here for this lemma. It is actually important that that happens. The reason is, think back to some of the functions that we used in our b of z 0, comma 1 example, the little point functions that jumped up at one point and were 0 elsewhere. What would you think the integrals of those functions would be? The integrals of those functions should be 0 because there's no real area underneath the curve there. So even though that function is somehow greater than 0 at a particular point, it still is not an integral of 0. So we need two things. One, the function f to be continuous, and two, the function to be strictly greater than 0, at least in some interval. In fact, I could even relax this a little bit. And if there exists an interval I such that the function f is greater than 0 on I, then this integral happens. Well, first, if f is not equal to 0 at any particular point on this function and it's continuous, it's going to be greater than 0 on an interval. And let's go through and show that. If f of x is greater than 0, then there exists a delta greater than 0, such that, notice I'm using an epsilon delta kind of thing here. I haven't quite said what epsilon is, but I'll show you in a little bit. There exists a delta greater than 0 such that the difference between, for if x and x naught is less than delta, then the difference between f of x and f of x naught is less than f of x over 2. You may remember this piece of an argument that was used in a previous video lecture, but I'm using that same thing again to say that the interval x naught, or let's make sure I get this right, then x, let's see, yeah. So then this interval of x minus delta and x plus delta is an interval where f of x is strictly greater than 0. Because any x value inside of this delta is at least is at most delta away from the point x, in which case I have that everything inside of here is only going to be half as far away from f of x as it is away from 0. So that tells us that it's all going to be inside of this little epsilon window, and hence that's going to be a positive value. We did talk about that a little bit in the previous video lecture. Unfortunately, the numbers escape from me right now, so I'll just give a quick picture here before moving on. Here, my little epsilon window looks like this. I have a point here, which this is greater than 0. So this is the value of f of x. And here is my epsilon window here of f of x over 2. It is half the distance away than it is from 0. So this gives us an interval here for this to be equal to. So if I needed to add that f is still greater than or equal to 0 here. So now what? What does this tell us here? If we have this lemma, now we have this interval here. So the integral from a to b of this function, f of x, if I'm looking at this function as if it is a non-negative function, well, then because there's only going to be positive areas wherever I can find them inside of this interval, I can always cut out parts of that interval so that I'm only taking a look at the integral of it over this interval I that I'm working on. So think I'm taking the interval from a to b and I'm just cutting it down to be the integral of I. Essentially, this is the area underneath the curve over which the x values are all inside of this interval, instead of all of the interval from a to b. you can see how that might just cut down the area that I'm working with. It's not a whole amount of area from A to B. It's just this stuff inside of this interval. But notice that the area under the curve over here has to be positive. And that is because, why? Something that is going to be bounded by is f of x over 2 times the distance between the endpoints of this measure I, basically the length of this measure I. If I had a kind of a way to write that, then I would write it more succinctly like that, but then the length of the interval I that I'm working with. Because every point on this function is at least f of x over 2. So if I think about how that area works, the area underneath this point right here is at least going to be equal to the area that I have right down here. And that's what's meant by this area. So because of this, I have something that is strictly greater than 0, and so I am good to go. So that's going to be our lemma for this argument. Maybe something that was a little bit clear to you, or something that you maybe could have gone through and constructed, but I wanted to give it because we're going to use it as part of this problem in the latter part of it. But now let's get back to utilizing the Weierstrass theorem, which says that, well, is there a way to use the fact that the polynomials are dense inside of this space to kind of get us to where we want to be? So let's see if we can do it. So first, f is a continuous function, and the integral of f of x times x to the n dx is equal to 0 for all of this. Let's keep going over here. I'm going to make a claim. And the claim is this, that the integral of f of x times p of x over this interval is also equal to 0, where p is a polynomial. And this might be immediate to some of you. Think if I multiplied this value by, or the function, or the x sub x to the n by a value of a sub n, then the integral value is still going to be 0. If I added an x to the n and an x to the m inside of here and replace this like x to the n times x to the n minus 1, well then because that's another exponent that I could be using there inside of that point, I could just break apart the integral into those two different parts, and that's equal to 0. And essentially, that's the whole idea behind this claim. The integral from a to b of f of x times p of x. So if p of x is, say, the sum as n goes from 0 to infinity of a sub n x to the n, or and I guess I should say to big N here, then this integral here is of f of x p of x is the same as the integral from a to b of this f of x times this sum, which gives me my polynomial. And because this is a finite sum, I can take it outside of my integral. So this becomes the sum as n goes from 0 to n of taking out the constants as well. I get a b f of x times x to the n dx. And because each of these is equal to 0, this whole thing is equal to 0. And that gives me that my integral of this function times any polynomial here actually ends up being 0 as well. Just think of this as kind of like breaking up the linear combination part of it. So we've got the integral of f of x times p of x is equal to 0. That's interesting because now we're going to get to use the fact that the polynomials are dense in x. So let's do this. Let's take a sequence of polynomials, and I'll call it p sub n, such that p sub n converges, and we get to say that this converges uniformly because we are looking at this being dense in the set of continuous functions on a compact interval, which is has a metric of rho, and that is that uniform convergence. So let's take a sequence of polynomials p sub n such that p sub n converge uniformly to the function f. It's important that they converge uniformly because what's going to happen when I take the integral? Then first, this should mean that f times p sub n converges uniformly to f squared. Notice that all I did was I multiplied both sides of this convergence here by the function f. Since f converges to f and p sub n converges to f, these sorts of things being bounded functions, we could go through and see that this indeed works out very nicely. By the way, if f was not bounded, we wouldn't be able to say this, but we can say it because f is bounded, and I'll leave the details to you. So if f times p sub n converges uniformly to f squared, then we know, and this is by last week's video lectures, that the integral from a to b of f times p sub n converges uniformly to the integral of f squared. But these are all equal to 0. So this is going to imply that the integral of f squared is greater or is equal to 0. Now I have a non-negative function, f squared, whose integral is equal to 0. And going through and taking the contrapositive of this statement, we have something which is not greater than 0, it is equal to 0. And hence, because we still have a continuous function that is, since we still have a continuous function that is non-negative, the only thing that cannot be true in this lemma, in forming the contrapositive, is that there cannot be an interval on this, where in a comma b, where this function is greater than 0 anywhere. So f squared is not greater than 0 on any interval by our lemma. So, in fact, f squared is equal to 0, which implies that f equals 0 as desired. So what this problem told us is it says that if you start with a function, continuous function, such that if you multiply that function by x to the n times any polynomial, in fact, and integrate that and get that's equal to 0, then there's only one possible function for which that's possible, and then that's the 0 function. That there's no other strange continuous function out there that allows us to do that. We needed something as strong as the polynomials being dense so that we could get this uniform convergence so that the integrals could converge the way that we wanted to. Notice that a lot of the different pieces are coming together in this particular lecture because we do want to build up to the Stone-Weierstrass theorem, which we're almost there to, and then to the Arzela-Ascoli theorem, which we'll talk about in the next video lecture. But this is a really kind of neat result. And in fact, it's not actually that rare to find results like this in the world of things related to the Stone-Weierstrass theorem. The fact that continuous functions on compact sets have a lot of things that work very nicely with them. In some sense, this is exactly what we want to have a set resemble, is to have these sorts of properties. But it turns out that that happens whenever you have continuous functions on a compact set. And notably, that compact set does not have to be in the real numbers. That compact set could be any metric space. Now, that is the extension of the Weierstrass theorem. Weierstrass theorem is only for polynomials being dense in a compact set of the real numbers. But what we can do is start extending this where X is any generic metric space. And so we define a few different things to get ready for the Stone-Weierstrass theorem in that regard. First, the space of polynomials is an example of an algebra of functions when considering things in the real numbers. But any subset of the bounded continuous functions of a metric space could be considered an algebra of functions. Now, for the sake of these examples, we're going to assume that our codomain is the real numbers. You can look back and see a little bit as to why we want that in the proof of Stone-Weierstrass. In particular, something important there is that we're able to show that given any two functions, that the max of those two functions and the min of those two functions is inside of this algebra. And that turns out to be quite important. Well, you can't define the max of functions or min of functions in a space without order. So just replacing the real numbers with a generic metric space y here is not going to be very good because it doesn't allow us to take a max or min of spaces, and we have to start doing other things. Stone-Weierstrass theorem, to be clear, is something that only has to deal with the codomain of the real numbers for its functions. What we ask for an algebra to be is a vector space with some extra stuff in there. We ask for it to be able to be closed underneath scalars, as well as addition of functions, or multiplication by scalars, as well as addition of functions. We also ask for it to be closed under multiplication of functions. This is the thing that separates vector spaces from algebras. Because we've talked about vector spaces before in a linear algebra context, but we haven't talked about algebras before. Maybe you've heard of algebra as the thing that you take in 7th grade, or maybe you've talked about algebra as something with homomorphisms and things like this in it in the graduate context. But the thing that separates these two objects of vector spaces and algebra is the ability to multiply the two elements inside of there and get something that is still inside of the space. So to kind of think about examples of things that are vector spaces but not algebras are things like R to the n. R to the n is not an algebra. This is a vector space that is not an algebra because there is no way, at least one that is in some like very neatly defined to take two vectors in Rn, multiply them, and get another vector in Rn. At least not in a way that we kind of maybe want to have happen for this. Now, you could go through and define perhaps a multiplication here, but R to the n does not come equipped with that sort of thing. So that's an important thing to distinguish. R to the n as a vector space is not an algebra, at least equipped with its typical operations. However, the polynomials is an algebra. Now that polynomials are not an algebra, if I do this piece of n, which we sometimes will talk about as the polynomials of degree less than or equal to n. We'll sometimes talk about this space like this. This space is a vector space because you can add polynomials of degree less than or equal to n and get something that's inside of this space still. You can scalar multiply a polynomial of degree less than or equal to n, but this is not an algebra. If n is greater than 0. So this is not an algebra. Whenever you consider anything that has an x in it, then you can multiply x times x and get x squared, and you could keep going and get as high a degree as you would like, even with just one polynomial with an x in it. So because of that, an algebra is a much more stringent requirement than just a vector space. It asks for all of the vector space constraints, but it asks also for there to be multiplication between any of the two vectors that you are able to multiply in there. Let's show that there are lots of good examples in the continuous functions with the real numbers as their codomain for where these algebras might apply. In fact, there's actually some good examples of closed algebras here too, and that's exactly what this example wants us to talk about. Let's fix a point A in this space X, X being the generic metric space that serves as the domain of our functions. And let's consider this set A, which is the set of all functions, continuous functions of X to R, such that f of A is equal to 0, where A is that fixed point. Then let's show that this is a closed algebra. So we need to show a few things. Well, one, we need to be able to show that if f of A is 0, then if f is continuous, if f and g are continuous functions from x to r, then we need to be able to show that first f plus g is in there. So about fg, and also cf, where c is a constant. We need to be able to say that all of these are inside of the space. I won't go through and prove that. I think we've kind of worked through that sort of thing enough. So these three things are indeed continuous functions. But what's more, we also need to be able to say that for each of these, f of a is equal to 0. So also, if f of a equals g of a equals 0, then f plus g of a is equal to 0. F times g of a is equal to 0, and c times f of a is equal to 0. This one, remember, is not composition, but that is not that, but that's actually good for us because this is actually the definition of the product of the two functions, f of a times g of a. And since both of these are 0, this is absolutely 0. And the rest are pretty natural to follow as well. So this shows that this set A is an algebra. In fact, it's closed if f sub n converges uniformly to a function f, and f sub n of a is equal to 0 for all n in the natural numbers, then f sub n of a has to converge to f of a. And that's due to the fact that this is for any point of convergence. In fact, uniform convergence is stronger than we need because we could even just say pointwise convergence to get that this will imply that f of a is equal to 0 as well. So if f sub n is inside of this algebra, and if f sub n converges to f and whatever the metric is, then this will imply that f is inside of this algebra as well. Of course, using the fact that continuous functions converging uniformly gives us continuous to say that f is continuous too, so that we can get this sort of closedness for it. So these have to be inside of A to make that work. There we go. So this is what we need to do to show something as a closed algebra to make all of this work. Okay, So both the set of polynomials and the set given on the previous slide do something called separating points, something that we talked about from our reading assignments, which says that essentially if you get two different x values, then there's going to be at least some point on that function so that the y values are different. Think, why is it called separating points? Because if you think about how the set of functions that we're looking at, let's call it A, views the x values that it's getting plugged into. If it's plugging in two x values and getting exactly the same y value, then it's kind of like it's treating those two x values as exactly the same, at least for a particular algebra that does not separate points. If, for example, every single function in that set sends f of A and f of B equal to something equal to 0, for example, and it's treating A and B as if they're exact same thing. A and B are the same type of function, or A are the same type of X value here. So to say something separates points means it gives you different Y values, is that from the perspective of the set, it treats them as if they are different. It wants to give different Y values to each of its different points. After using this definition, we can go through and generalize using some of the proofs that we see in some of the final sections here for the Stone-Weierstrass theorem. Now, I don't think I've even assigned this as one of our readings at this point. It is a reading for next week, but it is entirely optional because it's neat to get to see what these proofs look like. But this one in particular, I think even many seasoned mathematicians couldn't sit down and walk you through this proof. So I instead just give it as optional reading in case you'd like to take a look at it. Our focus in this particular class is going to be the power of Stone-Weierstrass theorem rather than taking a look at its proof. And the theorem says this. It says that if you have a compact metric space and a closed algebra of functions that separates points, then either the algebra is the algebra we were looking at before, this set of all functions would fix a specific point to be equal to 0, or it's the entire set of the continuous functions from x to r. If the algebra contains the unit function, for example, if it contains the function that is equivalent to 1 everywhere, that's what this notation is meant to mean. This is meant to mean equivalent as functions to 1. Then this algebra is in fact everything, because if it contains the unit function, then it cannot be in this set, because for that particular one, f of A would actually be 1 if I included the unit function in there, and that would break apart this entire set. What's neat about this theorem is that it only gives two choices. You only get the choice of it fixing a point at 0 or it being the entire set of continuous functions. That's a really powerful theorem, and it only comes from the fact that you need your set to be a closed algebra that separates points. Those three things: closed algebra that separates points, and if you want it to be the entire thing, with a unit function in there as well. There's in fact a theorem here that tells us how we get to use this typically. Typically, the way that we end up using this is we say that our algebras are not necessarily closed. But remember, you can take the closure of an algebra here, and it turns out that if you do the closure stuff, if you take the closure of an algebra, something like this, then you can get to either this set of all things that fix a point at 0 or that are dense inside of the entire space. So essentially, it's just saying that if we remove the closures here, then we're still okay, because we could just replace A being equal to these things with A being dense in one of these two things. And there's a small little bit of mathematics that accompanies this side of the theorem, but more or less it's a very similar thing. Our corollary follows directly from this way of thinking of the theorem. For example, the set of all polynomials is not closed in the continuous functions, but a countable subset of polynomials can be chosen such that the subset is dense in the continuous functions, and hence the continuous functions will be separable, because the set of polynomials is exactly this. It is an algebra of functions that separates points. It's a pretty neat thing that allows us to extend this Stone-Weierstrass theorem away from just taking a look at polynomials on a compact interval of the real numbers, and instead work on any compact metric space. Instead, again, instead of trying to focus on the proofs here, I want to go in and try to showcase the power here. So I'll go through this example here, and then I'll give a couple of hints on what I might do for the example that comes after it. Let's start with two compact metric spaces, x and y. Then I encourage you to take a look at the case why the Cartesian product of those two sets is also compact. The definition that I use for compact here to think about this is the sequential definition. Namely, if you have a sequence of elements inside of x cross y, see if you can show that this converges to a point inside of x cross y, even if it's just any type of sequence, using the fact that x and y are compact as individual sets. So let's take the algebra A to be the set of functions. h of x comma y is the finite sum of functions of all continuous functions, either going from x to r or going from y to r. So this is the sum of, like, think of this as the all sums of products of functions inside of here that are just single variable functions. F sub I of x, g sub I of y. Summing all of those together, where the things you're working with together are continuous functions. Let's show that this algebra is dense inside of the continuous functions. First, let's show that the algebra is actually inside of this space, because that's going to be important. Is this actually continuous? Well, H is the sum of these values here, S sub I, G sub I, where these are continuous functions. And the product of continuous functions, product of continuous functions is continuous, which allows us to say that each of these terms inside of here is continuous. And finally, the sum of continuous functions is continuous. And that allows us to say that this entire sum is continuous. So because all functions in this algebra are of this form, we have this inclusion as sets here. That's important. If it's going to be dense inside of there, it needs to be inside of there first. Now we can go through and start applying Stone-Weierstrass theorem. We need to start asking a few questions. Is this set in algebra? What happens when I try and go through and add sets functions of this form? What happens if I go through and try and add, say, h1 plus h2? Well, if I add h1 plus h2, I'm just adding in different parts of these functions. I'm going to basically take I equals 1 to n of f sub I 1 x, g sub I 1 x, and then do the same thing, summing over, say, values from 1 to n sub 2 of f sub j 2x and g sub j 2x. Now, you might be a little bit thrown off by my notation here, so let me clarify it. H sub 1 and H sub 2 each have their own functions here, which I'm notating as F sub 1 or F super 1 and G super 1, because my subscripts are kind of taken by these little indices given by this summation symbol. So the 1 here is coming from the fact that I'm looking at the functions that make up H1 or H2. Similar right here to the functions F and G, that F2 and G2 that make up those for H2. And if I sum all of those together, I still get a sum of products of single variable continuous functions. So that's definitely good to go. Similarly, I think we can see that C times F is absolutely good to go, because that constant could just be absolved into one of these functions, F sub I or G sub I, and it would still remain a continuous function. The last thing is H1 times H2. Now, this one's interesting. I can take a sum of these two types of functions, these F1 and G1 functions that come from the H1, gi1x, and then multiply them by these, which are the same types of functions that now work from the H2 function, and I could go through and multiply them together. Well, multiplying these together is going to do what? It's basically going to create a double sum here. The sum over from I goes from 1 to n1, and j goes from 1 to n2, of where you just go through and multiply each of these values together. And I'll go ahead and do a quick slight reordering here to make something pretty clear, which is that, needed to write these as y throughout. You may probably are screaming at your TV screens there. So here we go. This should be y, this should be y, this should be y, because it's y up here in particular. There we go. To make this a bit clearer as to why I'm doing this reordering, notice what I have now. On the left bracket, I have a function that is a single variable continuous function written only in terms of x. And on the right bracket, I have a single variable continuous function written only in terms of the variable y. And I'm multiplying those together and adding them together. This is another function that is inside of my algebra because of the way that I've written it. It is a sum of products of single variable functions, one function coming from x, one function coming from y. So that guarantees that this is an algebra. We have still a few other things that we have to go up here and discuss, which is making sure that it separates points. So does this separate points? Well, think There are definitely continuous functions on x and y separately that separate points. You can decide to create a continuous function that is 1 somewhere and 0 somewhere else. So you do have separation. Let f1, let's say it this way. Let's let f1 and f2 separate points on x, then choose g to be just the function that is equivalent to 1 everywhere. Then functions of the form f1x g y and f2x g y separate points x1y and x2y. So in particular, I want f1 and f2 to separate points x1 and x2 in x. And so those x1 and x2 are going to be separated by these two functions. If I go through and plug in x1y and x2y into these two functions, then you can see that what happens there is I get two different pairs to work on with there. You could do the same thing with the y components, and then finally, you know that at that point, you get two functions that work differently based on their x or their y values. There's a little bit more work maybe to try and make sure that when both of the x and the y are different, that it ends up working fine, but it's more or less, it more or less works very neatly in that way. The last thing we would need to show is that this is actually something that doesn't vanish everywhere. Does A vanish? And the answer is no, because I could just take f to be the one function, and I can make g be the one function as well. And I end up getting the unit function. And then Stone-Weierstrass is going to complete the proof. I have written entirely into this slide, and that was not my intention. I might try and clean it up before I end up going through and publishing this, but I have shown that this does not vanish anywhere. It is an algebra of functions that separates points. And hence I know that this algebra is dense inside of the continuous functions. The last problem here tells us that we can take the set of continuous functions and show the trigonometric polynomials are dense inside of this set. And I won't go through the whole part of this, but the reason that I give this problem to begin with is to say that those trigonometric polynomials we've been looking at before, sine of x, sine of 2x, sine of 3x, so on and so forth. Same thing with cosine of x, cosine of 2x, cosine of 3x. Basically, remember that trigonometric polynomials are linear combinations of things like this together with the function 1 over square root of 2. That all of these functions have some neat algebra properties as well. You might want to go through and try to make sense of some of these, but for the algebra part of it specifically, you're probably going to want to use the product of sum formulas. You may remember some of these, or at least maybe now that we take a look at them. For example, the fact that cosine mx times cosine nx is equal to 1/2 times cosine of m minus n times x, oops, not divided by 2, plus cosine of m plus n times x. So for example, product of sum formulas are useful for when I need to multiply different terms like these inside of the trigonometric polynomials. So just to be clear from the beginning to the end of this, recall that trigonometric polynomials are linear combinations of functions of this form. And that in order to show that this is an algebra, you can just see that you add these together and they work. You can scalar multiply and they work. Multiplying them together, though, is a little tricky until you recognize that once you use product to sum formulas on each of your products, you get them back into a sum of terms that are in this linear combination set of its trigonometric formula. All right. Then you could go through, check to see if these separate points, check to make sure that see if these vanish anywhere, and you'll eventually find out that these do not. So anyway, wanted to just kind of give you that little bit of a fact for these particular problems as we go through and start taking a look and applying Stone-Weierstrass in some other powerful ways. But we've had a very big day talking about bounded and bounded continuous functions. And so hopefully these sorts of examples are helping jog your memory a little or jog your spirit a little bit to see why we do this metric space stuff to begin with. These are some applications where we start seeing some really neat stuff take hold from what we've been doing so far in this class. But that'll do it for me today. Thank you so much. Have a wonderful day.